So, to understand quasi-projective variety, you have to understand what is the polynomial functions. You have to understand morphism between two quasi-projective varieties. But before studying morphism between quasi-projective varieties, you should understand what are the regular functions, like what are the maps to K. But like if you take just a polynomial, that will not give you a function, unlike affine case. Here you have to take some quotient, some rational functions. So that is the next goal. Functions on quasi-projective variety or regular functions. So whatever we have done should match, right? Because these are most general object now, quasi-projective variety. Whatever we have seen, regular functions for affine varieties, quasi-affine varieties, right? So whatever we are going to define is kind of a very general sense we have to do. So lemma, let y n is a quasi-projective variety. Quasi-projective variety. And you know that Pn you can write it as union of ui, but ui's are the standard open subsets, I equal to 0 to n. So then this P, if you let P be a point in y, so then this P will be a point in some ui, such that P belongs to ui. But ui is some affine space, right? So this ui has some identification with psi I or psi I inverse, whatever I define with an. So now suppose you have a function f from y to k. K means that the underlying field k be a function. As you have seen that when you define regular function, I am going to define regular functions. So regular at point P, I want to define. So if it is a regular at point P, what should be the definition? So you can do it in both language. You can do it as a projective variety, or you can think as it's because the point is in affine space. You can think this as a affine variety sense. So that's what is then the following are equivalent. F is any function. F is a function from y to k. So if you intersect with ui, the point P is in ui. Y to ui to k is regular function on affine subvariety. And the second one is that there exists a V open subset of Y containing P regular there exists containing P such that F is equal to G by H F equal to G by H, where G and H are homogeneous polynomial. No. That's not correct. Where G and H are homogeneous polynomial of same degree. On V. Of course, H of V not 0. If it is 0, it is not defined, right? The G mod H is not defined. So, see, point is that when I see a function or regular function, I want to define regular function at a point P. See, I can think this function in a, because this point is after all is a point in the affine space. So then I can think I can find a small neighborhood around that point which is in the affine space, such that if I f restrict to that open subset, it is a regular function on that small open set as a regular function on a affine variety, the quasi affine. But now this definition, this says that this open subset, this is in Y. Y is a projective variety. And this A, and in a small open subset of Y, this may go outside the UI. But it should look like G mod H, where G and H are so then, because G mod H is defined, because G and H are same degree and they are homogeneous polynomial. So G mod H perfectly, they are well defined on the projective, on points on projective space. So these two definitions. So this means that projective variety at a point, a regular function looks like G mod H, where degree G is same as degree of H. But that should match with the regular function at the affine as affine on an open subset in the affine space, because right. So that's why these two should be equivalent. Regular function on a quasi affine subset and quasi projective, and on a projective and an open subset of a projective variety, they should match. Otherwise, because quasi projective is kind of most general object. So that is what this is equivalent. This is when I am thinking as regular function on the affine variety, regular at a point as a on the affine variety, and this is the definition of regular at a point as a projective variety, regular. And first, so we will show that this is equivalent. So these two things are equivalent. Once they are equivalent, now you say that a function is regular if it is regular at every point. You understand? This projective variety, you can think as an open subset in a projective space, that's fine. But also you can think as there is a open further a smaller open subset which is lying inside UI, one of these UI. So this is how you should always think, that I can think as a affine, I mean locally I can think as a affine, also you have a projective variety, also it has a topology, you can think of a so these two are equivalent. So proof, maybe proof I will just write few lines, probably you can try. So first you prove that 2 implies 1. So take V in Y open such that, so V is a open subset of Y and P is in V, and this P is also in UI. So without loss of generality, I can assume this, I choose my V so that V is also in UI. You take V intersection UI for example. That's also an open subset in Y containing P, and that's also an open subset of, right? So such that V is in UI. So without loss of generality you can do. Then consider, and you know that this AF is G mod H on V, right? And H of V is not 0. So what will be the corresponding function? So you just dehomogenize G and H. So that will be, consider F to be the dehomogenize of F, G by so you consider this one. This will be a regular function because it is G mod H. After all, it's a polynomial, and this will be also, and this, since H is not 0, so it will be not 0 on this. So this will be regular on V, which will be regular on V. And conversely, suppose you have to be little careful here, but same here you have to homogenize, because here you have a function which is regular on a local open affine subset. So how do you make it a function on the projective, some subset of projective? You homogenize. So that same thing. 2 implies 1 and 1 implies 2 is that, suppose there exists V in UI intersection Y containing P such that F equal to G mod H with, of course, H of V is not 0. G and H are polynomial in n variable. So then you take, then you consider, so now two things can happen. One is the degree of G may be greater than equal to degree of H, or degree of H is less than degree of G, greater than equal to degree of G. Two things can happen, right? You don't have any control on degree. So then if this is the case, degree of G greater than equal to H, then you consider this xi. So suppose degree of G, I write it as D, and this I write it as E. So this is E, this is D. So then you consider xi. So this will be xi D minus E, or this is, you consider homogenize I of G by xi power D minus E homogenize I H, right? When you homogenize H, it will be a degree E polynomial, right? Degree E homogeneous polynomial, and then you multiply by xi power D minus E. So it will be a degree D, and this will be a degree D polynomial. So this makes sense. And if this is the case, then you take the other way around. Xi of E minus D homogenize G by homogenize H. So this is the, this is a way of, so this is when E greater than equal to D, and this is a, and this is G, and this is your G, and this is your H. This is G and this is H. Okay. So point is that when you think of a regular function at a point, you can think in two ways. One you can think is just as a affine regular function, which is or you can think as a quotient of same degree polynomial. Projective variety, the SY, it will be a K algebra. Yes, it is a K algebra. Not only K algebra, it has some grading, graded K algebra. I did not say anything about grading yet, but it will be a graded K algebra, and that played a role when we define proj of. See, in the case of affine variety, you have seen spec of A. So now in the case of projective variety, also it is called proj of some graded ring. So proj of graded ring means the elements are homogeneous prime ideals. See, in spec A, it's just a prime ideal, but here the elements are homogeneous prime ideals. Set of all? Yes. 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 But you have to take again degree 0. Degree 0 part of some localization. If you take an open subset, say D plus F, then it will be something like some polynomial by F powered something, but degree should, the degree of the numerator and degree of, that's how you define regular functions. So those things will come. Yeah, when I do more when I go ahead with regular functions, I will come. So now you say that if you have a function f, y is a quasi-projective, you say that f is regular if it is regular at every point. See, after all, regular function when we define, it is very local, right? You took a point and then you took a neighborhood and then you say that this is some polynomial g mod h, g by h. That's how you define regular function, even for affine case. But so now you say that it is regular. So globally there is no function now. See, when I say it's a regular function, there is no function globally. So regular means regular at a point P. So that means given by some u, comma, then you can give a function. So this always you put it in your head. When you say function, does not mean it is a global function. It's a local function. Locally it is given by some quotient of polynomials. So this is always, don't think that it is just like a two function. When you do projective, especially when you are doing projective case, projective variety, because there is no global coordinates. So this is important. And now last thing is that now if I take open subset U in Y is a quasi-projective, then I denote OYU, the regular functions. On U. And now it is a K algebra, because if you take two regular function, if they are quotient polynomial like f1 by g1, f2 by g2 at a point, then if you take the sum, then also it will be same because degree of f1 is same as degree of g1. So if degree of f1 g2 plus f2 g1 by g1 g2, degree will match. So they will be again regular. And if you multiply also, it will be like that. It is a regular function. And so it is a K algebra. In the affine case, also quasi-affine case, open subset of an, we saw that it's a K algebra. Even in quasi-projective also we saw, so this is again a structure shift. This will form a sheaf structure. This is called structure sheaf for the quasi-projective variety. Yeah, using this, yes. You don't abstractly. It is basically the structure sheaf and the proj of something.
What would be the bijection between spec and
Yeah, I'll come to that. Yeah. First, we've asked you to understand PN. How do you study PN? And then, so next, so this is a regular function and this is a K algebra. See, as you are growing older, you are seeing that functions are more important than the space. Functions has the functions and the behavior of functions, the kind of function you allow, they kind of control your varieties. If you understand functions on your space, you really understand the. That's why there is a subject called function analysis. Function analysis means you try to understand the functions on your topological space or whatever metric space, Banach space. So that's why functions are more important than, through function you want to study the space. So now we will see how can you, so like he is saying that there is some embedding. So how far you can do, and what is the map between quasi-projective varieties. So first we will see what is a map of quasi-projective variety. It should be something like same. It should be given by some n. If y1 is sub of Pn and y2 is in some Pm, then map should be given by some bunch of regular functions locally.